I thought I'd do one final video on Year 13 differentiation and just have some kind of bigger questions. So I've got 3 questions here. Feel free to read the question and have a go yourself before viewing the solution. But I think these will be good to show you, because these are kind of the questions that you'd more see in an exam, where you're not kind of guided through what differentiation technique you need to know, and just combining lots of differentiation knowledge together into one question. So my first example says the point P is the point of inflection of the curve y equals x squared minus 4x log x minus 1. Find the exact coordinate where the tangent to C at P intersects the x-axis. Okay, so the wording of the question implies that P is the only point of inflection on the curve, which means when we come to find the point of inflection, we should only have one point. And we're talking about the tangent at P, which is going to do that. And an interesting point is that a tangent and a point of inflection will actually appear to cross the curve rather than touch it. But that's just the nature of a point of inflection. So we're asked to find this point here where the tangent crosses the x-axis. The exact coordinate where the tangent crosses the x-axis, and we can see from the little sketch there that it should be slightly bigger than the number 1. Okay, so point of inflection, that should immediately ring bells that you need to double differentiate. So we're going to find the second derivative of this function. So the first derivative, dy by dx. Well, the first is just a nice year 12 differential. This is going to be a product. So we're going to do this times the differential of that, but the differential of that is 1 over x. So it's actually 4x times 1 over x, which is just 4. Plus that times the differential of this, but the differential of this is just minus 4. So we get minus 4 log x. And then we have the minus 1, which will differentiate to nothing. That's the first derivative. The second derivative, dy by dx, or sorry, d2y dx squared. The 2x will go to 2. The 4 disappears this time. And that's going to go to 4 divided by x. Now, for a point of inflection, we want d2y dx squared to be 0. And that occurs when x is 2, which kind of fits with the graph. We're looking for something a bit bigger than the number 1. So x is 2 will do the job. Okay, so when x is the number 2, y is going to be 4 minus 1, which is 3, minus 8 log 2. Minus 8 log 2. Okay, so that's the y coordinate of P. And then we're also going to need the gradient at that point. So y primed, I'm going to plug x as 2 into the derivative function, which is going to be 4 minus 4, which is 0, minus 4 log 2. So the gradient is minus 4 log 2. So these are the 3 pieces of knowledge I need to find the equation of the tangent. Okay, so a linear line that goes through this point and this point with the gradient of that is given by y minus the coordinate, y coordinate, so that's going to be 3 plus 8 log 2. And that's going to equal m, which is minus 4 log 2, into x minus x1, which is x minus 2. Now, if we want to find where this tangent cuts the x-axis, then we're going to want y to be 0. So x-axis intercept implies y equals 0. And that'll give us a nice equation for x. So we're going to get that minus 3 plus 8 log 2 is going to equal minus 4 log 2 plus 8, times x, times 8 log 2. The 8 logs 2 cancel out. I can divide that to the other side, and I get that the x-coordinate is going to be 3 divided by 4 log 2. And I wanted the exact coordinate. Okay, the calculator won't give you that as an exact answer, so you do have to do all the maths to get there. Therefore, the coordinate that I'm after is 3 over 4 log 2, 0. And that is where the graph cuts the x-axis. Let's just check that that number is indeed ever so slightly bigger than 1, which we expected from the graph. So if I do 3 divided by 4 log 2, we can see that it is slightly bigger than 1 as predicted. Okay. All right, second question. Here we have a rational function, which is a polynomial divided by a polynomial. The graph is y equals x plus 2, all divided by x minus 1 squared times x plus 1. So, part A is to find the exact coordinates of P and Q, which are the turning points on the curve. Okay, we've got a nice sketch of the curve over here. So we've got turning point P and turning point Q. And then part B of the question says to use gradient profiling to show that Q is a local maximum and P is a local minimum. Okay, so let's start with part A. Find the exact coordinates of P and Q, the turning points. So as soon as you see the phrase turning points, you need to immediately make links to that y primed is 0. So we're going to need to differentiate the function and set that to be 0 and then solve it. So this is a quotient. So we're going to have u, which is the top, x plus 2, and u primed is the derivative of that, which is the number 1. And then we're also going to have v, which is the bottom, which I'm going to multiply out the brackets. So I'm going to get x squared minus 2x plus 1 times x plus 1, which is going to be x cubed minus 2x squared plus 1 is minus x squared, minus 2x plus x is minus x, and then plus 1. And then I need to differentiate that to get v primed, which is going to be 3x squared minus 2x minus 1. Okay, so now we've got the 4 pieces I need for the differential, for the quotient. The quotient was given in the formula book. Y primed is going to be v u primed minus u v primed all over v squared. Okay, that's in the formula book. So I'm going to get dy by dx is going to be equal to v u prime, so that's going to be v times 1, which is just v. So that's x cubed minus x squared minus x plus 1 minus uv primed, which is going to be x plus 2 times 3x squared minus 2x minus 1. So all divided by, I'm just going to put v squared for now, because I've got some tidying up to do on the top first. So I could then multiply out the bracket. So I'm going to get x cubed minus x squared minus x plus 1 minus 3x squared. That's like cubed. You're going to get minus 2x squared plus 6x squared is 4x squared, but that's minus. Then I'm going to get minus x minus 4x, it's minus 5x, but minusing that's a plus 5x. And I've got minus 2, but I'm subtracting that, so plus 2. And that is going to be all divided by, again, it's going to keep it as v squared for a minute. And that's going to equal minus 2x cubed minus 5x squared plus 4x plus 3, all divided by v squared. Okay, at this point, I could try and find a factor of the cubic, but the calculators that you can take into the exam can solve cubics, and the exam would know this. Okay, so the cubic I want to solve, it's because I want to factorise it, minus 2x cubed minus 5x plus 4x plus 3, and that gives me these 3 roots. So I know then that x equals 1 is a factor, sorry, is a root, so x minus 1 is a factor, with the factor theorem. Minus a half, so that means 2x plus 1 is a factor. I've got 3 as well, so that means x plus 3 there is a factor. So those are the 3 linear factors of my cubic. I just need to check the coefficients of x cubed. X times 2x times x is positive 2x cubed, I want negative 2x cubed. So I just need to times that by minus 1, and there we go. That's now factorised. And that is all divided by v squared, which I'm now going to write in as, well, the original v, and I'm going to square it. So it's x minus 1 to the power 4 times x plus 1 squared. So x minus 1 to the power 4 times x plus 1 squared. Okay, so there's my derivative. Now, at this point, we tend to say, okay, well, I can set the top to be 0, and that will make the fraction 0. However, Notice that x minus 1 is actually a common factor to top and bottom, which means you can't just do that because you get x equals 1 as a solution, but there's an asymptote to x equals 1 on the original curve, so that's not going to work. So that's going to give me an incorrect solution. So let's just take out the x minus 1 from the top and bottom. And that leaves me with x minus 1 cubed now, times x plus 1. Okay, so that's my derivative. Now, I want to find the turning points of the curve, so I'm going to set y primed to be 0. And I'm expecting 2, because the graph alluded to that. There's a p and a q, one that's between minus 1 and 1, and one that is less than minus 2. This bracket is 0, which means x is minus a half, and that fits with the graph. You can see that p lies between minus 1 and 0, so that's good. And also x is minus 3 gives a solution as well. And again, we can see that that fits with this one here, q. So that gives me my x coordinates of my turning points. To get my y coordinates, I need to plug those two values into the original function. So if I go into computation mode on the calculator, I'm going to type minus 3 into there. Delete everything there. If I do minus 3, and then if I do answer plus 2 on the top, divided by answer minus 1 squared times answer plus 1, that's going to give me 1 over 32, which is 0.3125. So y equals 0.03125, that's exact, which we could have left as a 32nd. And then, because of the way I typed it into the calculator, if I change this answer up here now to minus a half, it will automatically recalculate, and that is 4/3. Could have used table mode as well, that would have also worked. Okay, so we got the x coordinates and the y coordinates, so now we need to state the coordinates. So p was when x was minus a half, so that has coordinates minus a half, 4/3, and we can see that's exact. And q, that was to the left of the left asymptote, so x is minus 3, and y is 1 over 32. And there we go. That finishes part A, the two coordinates of the turning points. Part B, use gradient profiling to show that Q is a local maximum and P is a local minimum. Okay, right, so just to recall, y primed, the differential of y with respect to x, was calculated as minus 2x plus 1 times x plus 3, all divided by x minus 1 cubed times x plus 1. Okay. Now, gradient profiling. We know that when x is minus 3, the gradient was 0. And we also know that when x was minus a half, the gradient was 0. So we need to choose a number that's less than minus 3, a number that's bigger than minus 3 but less than minus 1. There's an issue at minus 1 because there's an asymptote, so you need to break that gap there. A number between minus 1 and minus a half, and then a number between minus a half and positive 1. So the values I'm going to choose, just to keep things simple, is definitely going to be a 0 there, because it's easy to plug 0 into a function. Let's do minus 3/4. Let's do minus 2. And let's do minus 4. Okay, and I'm looking for the value of the gradient at these 4 points, and that will allow me to kind of sketch out roughly the shape of the curve, which will confirm that this is a maximum and this is a minimum. So, in my calculator, I'm going to go into table mode. I'm going to type in my derivative function, which was minus 2x plus 1 times x plus 3. And that's all divided by x minus 1 cubed times x plus 1 squared. So there was a squared there, I missed it off. Okay, so there's my function. I want to set the values. I want to start at -4. I'm going to go up as far as 0. And I'm going to move in steps of a quarter, if the memory will cope, so that I hit the -3/4. So 0.25. There'll be lots of numbers that a calculator will give me, which I'm not interested in. There we go. Good. So -4, and that is something positive. I don't actually care what the number is, but it's 0.006. The point is it's positive. And then the next one I'm interested in is -2. We can see that when x is -3, I've got a 0 gradient, which is good. Next is -2, I've got something negative, -1/9. So that's -0.1. Then I need to get to -3/4. It's going to have an error at -1 because there's an asymptote there. -3/4, we can see the gradient is negative, so it's -3.4. And then I need to scroll up to x is 0, and we can see the gradient is 3. Great. So that's all the information I need. And we can see that there's a positive gradient there, a 0 gradient there, and a negative gradient there. So therefore Q is a maximum. And here we've got a negative gradient there, a 0 gradient there, and a positive gradient there. So we can see that P is a minimum. Kind of see that shape there. So this is the point P. And this was the point Q. And we can see, therefore, Q is a local max. And P is a local min, which is what the graph alluded to, but the question asked us to confirm that using the algebra. Which is what we've done. Okay. And finally, my third question. This is a bit of a quicker one. Find the range of values of x for which the function y equals e to the cos x is convex, given that x is between 0 and 2 pi. So we're restricting the graph. It is only between 0 and 2 pi. I've got no idea necessarily what this graph looks like. So let's just punch through the algebra and see what happens. The first thing you need to decide is what convex means. And a convex curve is one that looks like this, or like that maybe. The point is the gradient is increasing. Okay, so the function is increasing, the gradient is increasing. It's gone from quite a negative to 0 to positive, so it's increasing, it's increasing, it's increasing. So that tells us that y double primed must be positive. Okay, the rate of change of the gradient is positive because the gradient is getting bigger. So that's what it means to be convex. Y double primed is positive. So we need to differentiate this twice. So the first step is to find dy by dx. And we're going to use the chain rule. Now, once you get really good at this, you can just write the answer down, but I will break it down here. So I'm going to say e to the u. That's going to differentiate to e to the u. So that's dy by du. And u is going to be cos x, so du by dx is going to be minus sine x. Therefore, dy by dx is the product of these two, okay, by the chain rule. So that is going to be negative sine of x times e to the cos x. Okay, that's the first derivative. The second derivative, d2y dx squared. We're going to need to look at this one and decide, okay, how we can differentiate that? Well, it's a product. Okay, it's a product rule now. So this times the differential of that plus that times the differential of this. So again, I'm just going to break that down over here. Once you get really good, you can just write the answer, but I'll break it down. So u equals minus sine x. U primed, therefore, is going to be minus the cosine of x. V will be e to the cos x. And that's actually the differential that we did up here. So we know that v primed is going to be minus sine of x, e to the cosine of x. Okay, and now we plug it into our formula, which is uv dashed plus vu dashed. So I'm going to get sine squared of x times e to the cos x plus that times that, so it's going to be minus cos x times e to the cos x. And we can factorise that out. So we get sine squared of x minus the cosine of x times e to the cos of x. Okay, so there's my second derivative function. And we want this to be positive. So what I'm going to do is I'm going to set that to be 0, first of all, to find the critical pieces. What we do know is this function is continuous. There's no asymptotes. So you don't have to worry about any dangerous points on the curve. E to the cos x can never be 0, because it's an exponential, so I can just ignore that. And I'm actually going to solve sine squared of x minus the cosine of x equals 0. But sine squared is 1 minus cos squared. So it's 1 minus cos squared of x minus cos of x equals 0. And then I can solve that quadratic in cos. So cos of x is going to equal minus b plus or minus the square root of b squared minus 4ac all divided by 2a. A is negative 2. There we go. So that is equal to minus a half plus or minus root 5 on 2. Okay, so those are my critical values, and let's find out what x values that gives. So if I punch arc cos, make sure you're in radian mode, so arc cos of minus a half, this side, plus root 5 over 2 is 0.9. 0.9045569, and we've also got the negative one as well. Not real. Have I done something wrong? I expected 2 answers to this question. Okay, let me just check my work. So y equals e to the u is cos x, so that differentiates to itself. Cos differentiates to minus sine, so dy by dx is the product of those two. Then we've got the product rule, that times the differential of this, which is that. This, yeah, so the minus sign comes down again, plus that times the differential of this, sine differentiates to cos, so that stays negative, so they equal sine squared minus cos is 0, 1 minus cos squared minus cos x is 0. Okay, all right, fine. I don't see anything wrong with that. Maybe there was only one solution, that's fine. So the other solution in the range then is going to be 2 pi minus that. So if I go back, oh, I must have deleted it. So if I do in 2 pi, subtract that number, which was arc cos of minus a half plus root 5 on 2. I get another solution which is 5.3786284113. Okay, so I just need to decide now if it's convex either side of those or convex in between those. So what I'm going to do is just choose a number in between them. It really doesn't matter what number, and find out if the second derivative is positive or negative. We know it's not 0 because it's only 0 at those 2 points. If it's positive between them, then I want all the x values between those 2 points. And if it's negative between those, then I want all the x values outside of those 2 points. Okay, those are the only 2 solutions between 0 and 2 pi, by the way. So let's choose the number 1, just because that's nice and easy to plug in. And I'm going to plug in the number, in fact, even better, plug in pi. Let's plug in pi into there, so that the sine squared disappears altogether, and we're left with just negative cos of x times e to the cos of x. Cos of pi is minus 1, so it's minus times minus, which is positive, e to the cos of pi, but cos of pi is minus 1, so it's just 1 over e. So at x equals pi, y double primed is 1 over e, which is bigger than 0. Therefore, it's convex at that point. Therefore, it's convex between those. 0.905 is less than x is less than 5.38, and that's three significant figures in each case. That's it. Less than 0.905, the curve will be concave, and bigger than 5.38, the curve will be concave.